Hello, and welcome back to the course. So we're going to look at primitives, antiderivatives. We're going to define what cycles are, sort of chains composed of closed paths, and we're going to look at the Cauchy theorem for derivatives or antiderivatives, depending on how you think of it. All right. So what is a primitive, an antiderivative? Well, if we, it's exactly that. It's we have a function little f, then an antiderivative or a primitive, a holomorphic primitive, but that's all, all the primitives and antiderivatives that we're going to be talking about are going to be holomorphic. So we're not going to keep saying that. So just a primitive. So if we have a function capital F, and it's holomorphic, so f prime exists everywhere, and f prime is equal to our little f, then capital F is a primitive of little f, right? That's what we mean by a primitive. Now, primitives don't always exist. They're going to locally exist, but globally they're not always going to exist. So not for every u and every f are you going to have a primitive, even if f is going to be holomorphic. We're going to show that locally we do have primitives, but for holomorphic functions. But globally it might not exist. However, if they do exist, then then they're the same up to a constant, right? So if you have two functions, capital F and capital G, and they have the same derivative, so they're the primitive of the same function, then, well, there could be a constant, right? Because the constant gets killed by the F prime, but that's it. And that's this is fairly easy to see. Just take F minus G, right? So that's an exercise, but very simple exercise. All right, so let's look at the fundamental term of calculus, right? We have antiderivatives, right? So we can talk about fundamental term of calculus, right? So if we have an open set and continuous function with a primitive, right? And if we have a piecewise C1 path, right, going from some gamma A to some gamma B, then the integral, the path integral, is just the primitive evaluated at the endpoints. Exactly what fundamental term of calculus in undergraduate calculus tells you, right? Except now it's a path, but yeah. Now, how does it work? Well, it's a very quick thing to prove. It is the fundamental term of calculus, after all. So we just write down this integral by definition, right? That's what by definition it's this guy, right? That's the definition of this symbol, or its set of symbols. And so now we look at what this is, and chain rule says that that's the derivative of this guy, the standard real derivative of this guy. Now it's a function of a real variable t, right? And it's complex valued, but that's fine. There's nothing wrong with that. So now we just apply the standard fundamental term of calculus, right? And we get, right, it's the antiderivative here is this guy, right? So we just plug in b and a and subtract, right? That's the standard fundamental term of calculus from calculus, right? So again, we used the chain rule, right, to go from here to here of a holomorphic function capital F composed with just a real differentiable function gamma, right? All right. So, right, and we're really applying it to real and imaginary parts. Now, maybe something that we're skipping a little bit, just just a little really tiny bit. It's you might think, well, I mean, this this thing is only defined, this is a piecewise C1 path, but that's not that's not really an issue here. This is this guy is nice and continuous, so yeah, everything's fine. You can check that's still fine, right? Or you could just apply it to each of the segments, and you're gonna have the the value of capital F. You're gonna add and then subtract it, right? So it's only the endpoints that really make a difference. Okay, so that's maybe was we were cheating just a little bit. All right, now something that I haven't made a big deal of yet, but we did assume it was that this little f was continuous, right? I mean, otherwise, this we don't know how to integrate this. Just there needs to be some integrability condition, right? And so we assumed continuous so that we could use we're basically doing everything with the Riemann integral, right? So continuity is good enough for integrability, right? So that's this continuity assumption is just so that this makes sense. It will turn out that this is still extraneous. If a function has a primitive, meaning if a function is a derivative of a holomorphic function, we will later on prove that function is actually holomorphic, right? So just being a derivative of holomorphic function will mean that the function is holomorphic. So it's definitely continuous. So holomorphic is, differentiable. Differentiable is means continuous. So it's definitely going to be continuous, right? So it's extraneous. But at this point, we don't have that. We have to add it to this theorem, right? So in the end, it's you could just once we're there, you could just say, and f is, you just cross out the continuous, and it's still true theorem, right? Maybe you need to change the grammar a little bit, right? Okay. Now, we want to integrate over chains that are sort of closed, and so those are called cycles, right? And how do we say closed? Well, we're going to say that a chain gamma is a cycle if it's equivalent to this chain over here, where gamma 1 through gamma n are closed piecewise C1 path, right? So they have to start and end at the same point. So that's what we mean by a cycle, right? It's a bunch of closed paths, right? And yeah, we can have a bunch of them, right? And we're adding them, or like adding multiples of them, and maybe subtracting them. But that's what we mean by a cycle, right? Sort of should be suggestive, right? Sort of goes around, right? And really doesn't, if we write down a cycle, right, it's just, we mean there is something equivalent to it, right? So for example, for the for the square that we saw before in 3.1, we wrote it as a single closed piecewise C1 path. Now we could also write it as equivalent to this chain composed of 4 paths. Now those are not, none of these are closed. Of course, they're just segments. But this chain is equivalent to a closed path. So this is a cycle, right? So sometimes it's useful to construct it out of other paths, right? You don't have to actually write it like this for a closed path, right? It's equivalent to something where all of those are closed paths. All right, now if gamma A is equal to gamma B, if we have a closed path, right, then you notice that in the fundamental theorem of calculus, we're subtracting the same thing, right? F of gamma A minus, F of gamma B minus F of gamma of A, right? And if gamma of A is equal to gamma of B, right, that goes away, right? We just get 0, right? So for a closed path, the integral of a derivative of a holomorphic function is 0, right? So the same thing for chains, right? For cycles, because, well, you just it's equivalent to something like this for a closed path. So you just do it for the closed path, right? For gamma 1 through gamma n, and for each one of those, we just get 0, right? So again, this continuous is extraneous. We'll show that that's not necessary, but basically, suppose that little f is a function which is a derivative of some holomorphic f on U, right? On some open U. And we have a gamma as a cycle in U, so something equivalent to something that's to a sum of closed piecewise C1 path. Then the integral over gamma is 0, right? So that's what I was saying in the previous lecture, right? Was the thing that a lot of times we're gonna have that for closed cycles, for a closed path, that we get that we're gonna get the integral being 0 for essentially all holomorphic functions, and so this is the version of that, right? So those kind of theorems are called Cauchy's theorem, and there's going to be a bunch of different versions that we're going to prove. So this is the first version that we prove. We're going to call it Cauchy's theorem for derivatives, right? Because basically we're saying that if little f is a derivative of a holomorphic function, then the integral over any cycle is 0. All right, now, so as I said, we'll prove a bunch of these. And usually there's going to be a restriction, on something. It's not always true that the integral of a holomorphic function over a cycle is 0. There's going to have to be some restriction. So usually it's going to be on U. It's essentially going to be, there are no holes in U, is essentially the restriction. Or it's about gamma, and that's just going to be, gamma doesn't go around any holes, right? That's essentially, going to be what the restrictions are going to be. But those are that's really what we want. Because really, the Cauchy's theorem is something that's that you can think of as defining the primitive, right? So usually it goes that you have, if you have a version of Cauchy's theorem, then you can write down a function by writing it as an integral, which will mean that basically we're writing the antiderivative, right? And so if we could do it for any gamma, we would actually have a primitive. And so usually it sort of goes the other way, right? But it also means that we have to have, there has to be some restriction on this, right? Either on the functions or on the U's or on the gammas, right? So in this version that we proved, we restricted the functions. We said they have to be derivatives of holomorphic functions. Now, the final thing, and in this lecture, is this gives us actually a very sort of appealing version of Cauchy's theorem. It will be subsumed in the later versions, but at this point, it's actually kind of neat. If we have any polynomial, so polynomial in Z, so it's a holomorphic polynomial, right? Just in Z. And any cycle in the complex plane, any cycle whatsoever, then the integral over that cycle will be 0 of the polynomial, right? So for polynomials, we get Cauchy's theorem, right? So that's again, putting a restriction on the functions. And that's I'll give you a hint on the exercise is you can always find an antiderivative, right? A calculus student can find an antiderivative. All right, so next time what we're gonna do is we're gonna prove a sort of a special version of Cauchy's theorem. It's called Cauchy-Gaursat theorem, sort of Cauchy for triangles. But the big thing there is going to be actually, what are the assumptions in the proof, and so that it's going to make that's going to make everything that we do possible, and it's it's Cauchy-Gaursat because we're not going to assume continuity of the derivative. Which makes everything just a little bit harder. But basically, it's going to be Cauchy for triangles, right? It's just that way you can think about it. All right, so see you next time.